Good morning, everybody. Crank this up for a second.
Emma, nothing. How are you going to do this?
All right, I'm going to give people about 2 minutes, and then we will start the lecture.
Well, now it looks like since everyone wants to tell me to do it wrong, we're going to do it again. This right here is rainwater charged in the full moon.
Close this. And I want speaker view. Keep it clean. All right. All right. I want to open up your online resources. All right, let me share this screen for a second. Annotate, draw. Okay, so just a couple of quick things before I start the lecture. Where's my pen? So one, I don't know if you've got this email, but we are definitely not opening up campus. And so we are doing online for the rest of the semester and also for the summer. A couple things in terms of what's due this week. Here is the schedule for this week. So Tuesday, tomorrow, chapter or PLC number 8 and 9 due, uploaded to Mastering Physics. Again, I'll show you where in a second. Wednesday, labs 5, 6, and 7 due. Again, uploaded to Mastering Physics. Thursday, chapter 9 homework due. Friday, quiz on chapter 9. Let me do a new share. That's not what I want. Hold on 1 second. Launch. Mouse. I want course home. Clear all drawings. Okay, having a technical difficulty for a second. Why can't I invite clear all drawings? Okay, so just as a reminder in terms of where to turn stuff in on your document sharing section. So what I did is I created links for all the different labs. And so let's say you are in the 8 a.m. lab. To turn in your PLCs, you would just click this link. And to turn in your labs, you would just click this link. And then, let me stop this for a second and do another share. Document sharing. Stop that for a second. Online resources. Share. Okay, so just in terms of uploading the PLCs and labs, what I noticed was that when I download everything to grade it, it erases the owner information. So if you don't have your name on your PLC or lab, then it's really hard for me to figure out who did what. So what I'm asking you to do for the naming scheme is just to name your assignments last name, first name, assignment, and then page number. So for example, PLC number 8, I might do McCullough _Joe _ PLC 8 _ page 1 or page 2 or anything like that. So that's that. Let me clear all drawings, stop this share. And then before I start the lecture, I just want to quickly open it up for questions about turning in PLCs or labs or anything like that. And one other thing, I'll send out an email just so there's no confusion. The times in Mastering Physics are Eastern Standard Time. And so if something's due on Friday, it's really due by 9 p.m. California time on Fridays. Okay, So let me open it up. Anybody have a question about just turning in stuff that I can answer? Going once.
I have a question.
Okay, Carolina, what's up?
What if you turn something into like the PLC section and then you accidentally upload the wrong file? I tried to see if I could delete it, and like, how can you delete it if you've uploaded it already?
If you uploaded a wrong file, just upload the new one and I can figure it out from there. So you're saying you couldn't delete the old wrong file from the uploads?
Right.
Yeah, so if that's the case, just upload the new file and maybe name it something so it's obvious that this is a newer one.
Okay, sounds good.
Anything else? If not, I'm going to go to lecture. Okay, one other thing, just so you know, and I'll send this out as an email. The labs that we're doing for the next 2 weeks. This week, I was going to do a 2 or 3 part lab on conservation of energy. Next week, a lab on conservation of momentum. The more I thought about it, these labs are a bit challenging. It's me filming it and then you just watching it and taking data. So what I decided to do is for the next 2 weeks, I'm only going to do 1 part of each lab. So tomorrow or Wednesday, 1 part of conservation of energy. Next week, I'll do a 2nd part of conservation of energy. And what I'm going to do is keep the next 2 labs pretty short. Literally, you should be able to do everything in an hour and then upload an additional lecture. So on Wednesday, there'll be an additional lecture. And then same thing next Wednesday. Okay, so let me share this screen with you. And let's do a little recap. Okay, so also I'm going to try and keep these recaps shorter. What I think I'm going to do is on Wednesday when I record an additional lecture, I'm going to do sort of a big giant recap and then do some example problems and things like that. So just real quickly, what we've covered so far is, let's just see here, quick chat. Why can't I see it? Recap. I'll be right back. All right, off with my haven't showered hat. On with the recap. Okay, so started off talking about just the dot product. I'm just going to tell you again, dot product is a product of 2 vectors. The end result is a scalar. It is not a vector. It just has a number plus units. The way the dot product is defined is, make this a little bit bigger, dot product of any 2 vectors is the magnitude of 1 vector times the magnitude of a 2nd vector times the angle between the 2. From that definition, you can show that any unit vector dotted with itself, the end result is 1. Any unit vector dotted with the 2nd unit vector, the end result is 0. From that, which you can show as a 2nd way of getting the dot product of 2 vectors, is multiplying the x components together, multiplying the y components together, multiplying the z components together, and then adding them up. Our basic energy model. Can't do that, I hate that. Mouse. Why is this not letting me move? Technical difficulties. Mouse. Everybody select. It's not letting me do this. Aha. All right, I'm going to stop this share for a second because I'm experiencing technical difficulties. Go back to this. External, blah, 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 blah. Okay, sorry about that. Sharing this again. Share screen. Share. Okay, and then, oh, I know. I want to annotate, not using that. I want to use this. Okay, so in our basic energy model, we have a system defined by U. The reason the definition of the system is important because any forces from outside the system being exerted on the system is called an external force, and that will affect the total energy of the system. So within a system, objects within the system can exert forces on each other. They're called internal forces. They don't affect the total energy of the system. How I affect the total energy of the system is doing work on the system. If I do positive work or a force does positive work, that force is adding energy to the system. If that force does negative work, that force is removing energy from the system. Our big sort of energy model is this. It says the change in energy of a system is equal to the work done by all external forces. So this right here is the sum of work done by all external forces. Okay, so this is it. The change in energy of a system, and this is the change in total energy of the system. Just so you know, right now we're just dealing with particles. The only form of energy we're really looking at is kinetic energy. We're assuming that these particles aren't interacting with each other. Next chapter, chapter 10, we're going to start looking at potential energy, gravitational potential energy, elastic potential energy, and so on. Right now, I just kind of gave you some definitions of the kinds of energies we're going to be looking at. We're not dealing with them mathematically. So then what I showed you was that from sum of the forces equals ma, we basically derive this equation that says the integral of fx dx from x initial to x final equals 1/2 mv final squared minus 1/2 mv initial squared. In this equation, this is our definition of work. So work for any force is defined as the integral of fx dx from x initial to x final. This equation always, always, always applies. I'm going to look in a second about what happens if the force is constant. But this equation will always apply for work. So this is a force doing work on the system, which is changing this quantity. We have some final minus some initial. Since the total work done on a system changes the energy of the system, this quantity, 1/2 mv squared, must be this energy of motion. So we define kinetic energy as 1/2 the mass times the speed squared. M, mass in kilogram. V is speed, not velocity. And then again, just from this equation, 1, kinetic energy. Whoops. Kinetic energy has to have units of mass times speed squared. So mass has units of kilograms, speed has units of meters per second, but we're squaring that. So kinetic energy has units of kilogram, meter squared per second squared, which we're going to see is basically a joule. Okay, and then I did this example problem. What I want to do now is work done by a constant force. So constant force basically means F is constant in magnitude and direction. So we are only looking right now at forces that have a constant magnitude and a constant direction. So let me stop this share for 1 second and just open it up for a minute or two about a little recap of anything that I've done so far in terms of work, kinetic energy, energy model, things like that. Going once, going twice, recap coming off. Party hat coming on. Okay, sharing the screen again. Share. Okay, so let me make this a little bit smaller. So what we're going to do now is consider a, kind of right here, but I'll just draw this again. Let's just say I have a box. Let me draw this. So let's just say here is a, where am I? And let me make this red. Draw. So let's say I've got a box. Starts here. I'm exerting a force on it, F. And the box moves to the right. So my displacement, I'm starting here, ending here. My displacement in the x direction, delta x, points to the right. And let's just say that this angle here is theta and F is constant. So the magnitude of the force is, the magnitude of the force is not changing. The direction of the force is not changing. Because this force is being exerted in the same direction of motion, that means the acceleration is pointing in the same direction of motion, which means it's speeding up. So initially, this particle has, or this box has some speed. A force is applied over this displacement delta x, causing the kinetic energy of the object to increase. So let's just figure out what is the work done by this constant force. So again, this equation, work equals the integral of fx dx from x initial to x final, always, always, always applies. In this particular case, my force in the x direction, if I look back up, here's F, here's theta, here's my force in the x direction, Fx. This is the adjacent side, which means it's cosine. So this integral of Fx dx becomes the integral of F, becomes the integral of, let me erase that little part, x final, so of F times the cosine of theta times dx. So here's the thing, F is constant, the angle is constant, which means I'm taking the integral of this F cosine theta dx, where F and cosine theta are both constant. So I can pull them out of the integral, and this becomes F times cosine of theta times the integral of x initial to x final dx. Integral of dx is just x, so this becomes F cosine of theta times x evaluated from x initial to x final, which is basically my delta x. So what I get is, for a constant force, work equals F times delta x times cosine of the angle between them. So this is if the force is acting in the x direction. And just from our definition of the dot product, where the dot product is the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between them, what we get is our most general case for the work done by a constant force is the dot product of F dotted into the displacement. We're going to use delta R just because this could be in the x direction or y direction or z direction. But here is the definition of work for a constant force. The only time you can use this equation is if you know the force is constant in both magnitude and direction. So the work done by a constant force, the force dotted into the displacement. So a few things about this. Let me go to a different section here, new section. Okay, so if the work done by a constant force is F dot the displacement, keep in mind this is the magnitude of F times the magnitude of the displacement, delta R, times the cosine of the angle between the two. You could use theta or alpha, either one. Magnitude of F is always positive. Magnitude of delta R is always positive. So the only thing that can make the work positive, negative, or zero is the angle between the force and the displacement. If that angle is greater than or equal to 0, but less than 90 degrees, then the work done by that force is positive, and that force is adding energy. to the system. If the angle between that force and the displacement is 90 degrees, then that force is not doing any work. No energy is added or removed. So no energy added or removed by that force. And then if the angle is greater than 90 degrees, but less than or equal to 180 degrees, the work done by that force is negative because the cosine of the angle is negative, which means that particular force is removing energy from system. So this is the equation you're going to be using a lot. The only time you're going to end up using work equals the integral of fx dx. Two cases. One, if they give you a plot of force versus x, and you have to figure out the area under the curve to get the work. Second one we'll look at tomorrow, a force from a spring is not constant because it depends upon how much the spring is stretched or compressed, which means the work done by a spring, I can't use this equation because this is only for forces that are constant in both magnitude and direction. Okay, let me clicker question here for a second. So thinking about this whole definition of work being the dot product of the force dotted with the displacement, I want to take a look at clicker question 7.3. Clicker question 7.3 says the following. Figure shows 4 situations in which a force acts on a box while the box slides rightward a distance d across a frictionless floor. So in all of these cases, this box is, sliding to the right. So my displacement is to the right. The magnitudes of the forces are identical. Their orientations are as shown. Rank the situations according to the work done on the box during the displacement from most positive to most negative. So all 4 cases, the box is moving to the right. Force is the same in each case. The only difference is the angle that the force is applied at. So take about a minute, see if you can reason this through. What is the work done from most positive to most negative? Chris, you got a question? Christopher, you got a question? I see your hand raised. Going once. Let's see, chat. All right, what's your question? My microphone isn't working. Okay. Is anybody's, I muted people just when they were coming in. Can anybody unmute yourselves? Let me know that somebody's microphone is working.
Mine's on.
Okay.
Yeah, I'm good.
Okay, is the distance the same in all? So in this case, for this particular clicker question, in all 4 cases, the box is moving the exact same distance to the right. So given that, rank these 4 different forces by how much work they do from most positive to most negative. And again, let's see if, well, you can't really vote easily, but take a minute, think about it, and then we'll go through it in 30 seconds. Draw here, draw. Hey, spoiler. Spoiler alert. Okay, so in this particular clicker question, you're basically told that F is the same in each case. The force has the same magnitude. Delta R is the same in each case, so the only difference is just the angle between the force and the displacement. In case D, my angle is going to be 0 degrees. Cosine of 0 is 1, so that's the most work you could possibly do. For C, I don't know what the angle is, but I do know it's somewhere between 0 and 90 degrees, which means the work done is going to be positive because I'm taking the cosine of an angle between 0 and 90. In case B, my angle is going to be 90 degrees. So this one, I know the work is going to be 0. I know for D, the work is going to be greater than 0, and it's going to be the most positive work you can do. Case C, the work is greater than 0, but less than in case D. And then for case A, I don't know what the angle is, but this thing is moving to the right. The angle is somewhere between 90 degrees and 180 degrees, which means the work done is going to be negative. So D does the most positive work. C does positive work, but less than in case D. In B, the angle is 90 degrees, so the work done is 0. And then for A, angles between 90 and 180, so the work done is negative. Whoop, whoop. Okay, let's take a look at an example problem or two. So let's first do a relatively easy one. So this is problem 919. Problem 919. So the 3 ropes shown in the bird's eye view of the figure below are used to drag a crate 3 meters across the floor. How much work is done by each of the 3 forces? So here again, the thing that matters is the angle between the force and the displacement. All of these forces are constant, so we're just going to use work equals F dot delta R. So it's going to be the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the displacement. In all 3 cases, this thing is moving to the right. Delta X equals 3 meters. So what I want to do is just real quickly have you think about what is the angle between tension 1 and the displacement? What is the angle between tension 2 and the displacement? What is the angle between tension 3 and the displacement? So take it just 30 seconds. What angle am I going to use when I'm calculating the work done in this problem for tension 1, for tension 2, and for tension 3? What do you think? Okay, and so if I'm ever unclear, I always just like to draw a little diagram. And again, this is not a free body diagram. I'm just trying to draw the 2 vectors together so we can see the angle between them. So for tension 1, the displacement is to the right. Here's my delta X. The force, T1, is up at an angle. The angle between those 2 is 20 degrees. So the angle I would use for calculating the work done by tension 1 is 20 degrees. Tension 2, again, the displacement in all 3 cases is to the right, but now this force is down, at an angle of, this is T2, 30 degrees. So the angle I would use for calculating the work would be 30 degrees. And then for T3, I'll do that one over here. Again, the displacement is to the right, delta X, but my force in this case is to the left. The angle between those is 180 degrees. So the angle I would use would be 180 degrees. So once you've calculated or once you've figured out what is the angle between each force and the displacement, it's really from this point just plugging and chugging. Let me make this a little smaller for a second. Okay, and then do the work right here. So the work done by our first force, tension 1, is just going to be the magnitude of the force, T1, times the magnitude of the displacement, delta X, times the cosine of the angle between the 2. So for force 1, tension was 600 newtons. We were told the displacement was 3 meters. And we've got our angle, 1 second, Omar, is 20 degrees. So what I get for the work done by tension 1, let me just look at the answer so I don't have to put this in the calculator, assuming that the book answer is right. What I get for 1 is 1.7 kilojoules, or 1.7 times 10 to the 3 joules. All right, let me pause and check out this question chat. How do you raise your hand? Click. So yeah, if you want to raise your hand, click on participants. And then underneath the participants, you'll see a little button that says raise your hand. Okay, so for force 2, tension 2, and let me just jump straight to the case. It's going to be the magnitude of tension 2, which is 410 newtons, times the displacement, which is 3 meters, times the cosine of the angle between tension 2 and the displacement, which is 30 degrees, which you're going to get for the work done by tension 2 is 1.1 kilojoules. And then last but not least, the work done by force 3, tension 3. In this case, the tension is 660 newtons. 660 newtons. The displacement, again, is 3 meters. And in this time, the angle is 180 degrees. 180 degrees. What you'll get for the work done by this force is -2 kilojoules. So work done by force 1, 1.7 kilojoules. Work done by force 2, 1.1 kilojoules. Work done by force 3, -2 kilojoules. So here's a quick little question for you. What is the end result of these three forces doing work? How is the total energy of this, this crate going to change? What do you think? I've got three forces all doing work. Each one does a different amount of work. What is the end result? Well, the end result is that the total work done, now this is not part of the question, just this is in addition to it. The total work done by all external forces equals the change in the energy of the system. So my total work done is 1.7 kilojoules plus 1.1 kilojoules plus -2 kilojoules. So in this case, the total work done is what? 2.8 kilojoules minus 2, I get 0.8 kilojoules of work total. What that means is that the total energy of this system is going to change by that amount. In this case, the kinetic energy of the crate is increasing because we're doing positive total work on it, resulting in that energy increasing. All right, let me pause this. Well, let me just keep the share open, but let me open it up for a minute for questions that I can answer about this. So work done by a constant force, I can use this equation, work equals the force dotted with the displacement. Whether that work is positive, negative, or zero only depends upon the angle between the force and the displacement. All right, let me pause, open up questions for a minute. Okay, next thing I want to look at then is the work done by gravity. Let me go back to lecture notes first. Actually, let me just do this in a new section. We'll scroll down. Scroll down here. Okay, so we're going to do work done by gravity. Can I make it home? Okay, so one, gravity is constant. We're considering the force of gravity, our weight is just equal to mg. That is not changing. Gravity always acts straight down. The force is always mg, which means the work done by gravity is going to be constant. So I could just use, why can't I scroll down? Since this force is constant, if I want the work done by gravity, I could just use it's equal to the force of gravity, or the weight, times my displacement, times the cosine of the angle between the two. So let's say something starts here at some initial height and ends here at some final height. So my displacement points straight up, and I'm just calling it delta y. So this might be me lifting a box up from this initial height to some final height. If I want to know what is the work done by gravity, it's just the force of gravity times the displacement times the cosine of the angle between the two. In this particular case, this thing is being displaced straight up but the force of gravity, mg, is straight down. So the angle between the force of gravity and the displacement when I'm lifting something up is 180 degrees. So if I want to calculate the work done by gravity, it's going to be the force of gravity, mg, times the displacement, delta y, times the angle between the two, which is 180 degrees. Since this equals -1, what I get is the work done by gravity is negative mg delta y. Let me pause, look at the question in chat. Should we always use kilojoules? So no, the unit of work, the unit of energy is joules. It's just the answer was 1.1 times 10 to the 3 joules, 1100 joules, or 1.1 kilojoules. So you could write it out as 10 to the 3, you could write it out as kilojoules. So a couple things about this. Let me go. So this equation is the work done by gravity. Oops. Work done by gravity.
Hey Joe, can you go up a little bit? Yeah, it looks good.
There we go. Work done is negative mg delta y. Okay, couple things about this. If delta y is greater than 0, so if the elevation is increasing, the work done by gravity is actually less than 0. And if delta y is less than 0, so I'm decreasing in height, then the work done by gravity is greater than 0. Let me check this out real quick. That's how we all feel. I don't know about you. This is a very trying time. I know you guys have probably gotten a bazillion emails. I can't tell you how many emails I've gotten. Yeah, this is sort of a new paradigm for all of us. This is kind of working for me. I've got this pen that's got a little button on it, and every time I hit the, anyway. So, a couple things about work done by gravity. So this one equation is the equation we're going to be using. Work done by gravity is negative mg delta y. So one important thing, and this is going to help you with a PLC question, is gravity is a conservative force. This is from chapter 10 that we're going to cover, but there's two important things about conservative forces. One, let me just say, in physics 4A, you're only going to see two conservative forces. One of them is gravity. The other one is the elastic force from a spring. Thing about conservative forces, there's two important things. One, the work is path independent. What that means is the following. It doesn't matter the path you take. All that matters is where you start and where you finish. So for example, if I lift an object up from here, my initial position, to my final position, the amount of gravity, the amount of work that gravity does if I lift it straight up is exactly the same as the amount of work if I take some kind of weird curved path. And I kind of show you why that's true. But it's really nice because I don't have to worry about how an object got from one position to another. All I care about is initial position, final position, and the work done is only going to depend upon where you start and where you finish. Second thing about conservative force is you can define a potential energy. So I mentioned we're going to look at two specific kinds of potential energy. One's gravitational potential energy. The other one's elastic potential energy. The reason we can define potential energies for those two functions, those two forces, is because they are conservative forces. So let me just touch on, was there, somebody raised their hand, I saw. Question? No? Okay. So let's take a look, for example. Let's say I pick an object up and I lift the box, let's say, from this position to this position. My delta y is straight up. My work done by gravity is just going to be negative mg delta y. Well, what happens if instead of lifting it straight up like that, let me scroll down a little bit. So in one case, I'm lifting this from here to here, straight up. Now let's just say I'm starting from that same height and ending at that same height. But now instead of going straight up, let's say I go sideways, and then I go up, and then I go this way, whoops, and then I go straight up, and then I go here, and then I go down. And let me label these: 1, 2, 3, 4, 5, 6. If I calculate the total work done by gravity in all 6 of these little segments and I add them all up, I'm going to get the exact same work done as if I just started here and ended here. And the reason is one, anytime I'm moving sideways, gravity is not doing any work because the angle between gravity and the displacement is 90 degrees. So in cases 1, 3, and 5, 1, 3, and 5, 1, 3, and 5, the work done by gravity is equal to 0. Anytime an object is increasing in elevation, the work done by gravity is negative. Anytime it's decreasing in elevation, the work done by gravity is positive. So in case 2, the elevation is increasing, the work done by gravity is negative. Case 4, the work done by gravity is negative again because I'm increasing in elevation. So in cases 2 and 4, the work done by gravity is less than 0. And then in case 6, where it's moving downwards, now the work done by gravity is greater than 0. But here's the thing: if I calculate the work done in part 1 plus the work done in part 2 plus the work done in part 3 plus the work done in part 4 plus the work done in part 5 plus the work done in part 6, what I'm going to get is exactly the same answer as if I just started from my initial position and ended in my final position. It does not matter which path I take. Sometimes gravity is going to be doing no work. Sometimes it's going to be doing positive work. Sometimes it's going to be doing negative work. But if I add up the work done in all the little segments, it's exactly the same as if I just started from my initial position, ended in my final position, just moving it straight up. So the amount of work done by gravity in going from here to here. If I go straight up, I do a certain amount of work. If instead of going straight up, I take some weird convoluted paths and I add it up, believe it or not, both of those paths are going to give me the exact same amount of work. So to simplify it, the work done by gravity is negative mg delta y. And this is always going to apply. It doesn't matter which path you're taking. So this is path independent. Whoops, path independent. Okay, let me pause for a second. Let me just stop this share and open it up for any questions that you may have about work.
Hey, Joe,
Yes.
can you show again on the little diagram when you have the 1 through 6? I missed something.
Right
Please.
here? Oh, let me share that again then. Share screen. Okay, this diagram right here.
Yes, thank you.
So yeah, what I'm just showing here is that for gravity, all I care about is where the object starts, where it finishes. I don't care about the path it took to get from its initial position to the final position. The work done by gravity only going to depend upon where it starts where it finishes, and that's only true because gravity is a conservative force. And what defines a conservative force are these two things. And again, it's a sort of little preview of chapter 10. The work is path independent, which means it doesn't matter how you get from your initial to your final position, and you can define a potential energy function. All right,
Or Joe,
Omar.
I just have one more question. For this class, is the force ever gonna change, or is it always gonna be constant?
For the force of gravity?
No, like the force, like when we're pulling something, like if we would say like, oh, you're pulling a car and then you accelerate or something like that.
No, so that's for the most part, if we're doing like tension or gravity or something like that, that force will be constant. The one force that's going to come up a lot, we're going to see this basically on Tuesday, where the force is not constant, is if I have an object connected to a spring. So let's just say this is where the spring is not stretched or compressed. So this is where the spring is unstretched or uncompressed. If I then stretch this spring out, one, the spring is always going to exert a force back towards its equilibrium position. But the force that the spring exerts, what we're going to see is negative some constant called the spring constant times the displacement, which means as I stretch a spring farther and farther and farther, delta x gets bigger and bigger and bigger, so does the force that the spring exerts. So a spring never exerts a constant force. The whole time the spring is being stretched or compressed, how much force it exerts depends upon how much the spring is stretched or compressed, which means when you're figuring out the work done by a spring, you cannot use F dot delta R because the force of the spring is not constant. Basically, what you're going to have to do, and we'll see this tomorrow, the work done by a spring, I'm going to have to integrate from x initial to x final of fx dx. Keep in mind, this equation for work always applies, and it's only if I have a constant force that I can use F dot delta R. Okay, if there's no other questions on this, Christopher.
Yeah, so if all the energy the work is doing is being put into kinetic energy, then the change in kinetic energy should be equal to the work, right?
Yes, so right now in this chapter, we're not yet looking at potential energy functions. So we're just looking at, so the total work done on a system is going to result in the energy of that system changing. And right now we're just looking at kinetic energy. We haven't started looking at potential energies or thermal energy or anything like that.
Mm-hmm.
Okay, so I want to stop this share for a second and then open up your PLC real quick. Physics for
Joe?
Yes.
What time is the PLC due? Tuesday?
Tuesdays, let's just say everything could be due by 9 p.m.
Okay.
All right, does anybody remember offhand let me just look up, sorry, for a sec, Joe's homepage. PLC activities, work in kinetic energy. So this was Physlit problem 6.4, document sharing. Joe McCullough, 6.4, sorry about this. PLC activities, links to Physlit. Mechanics, 6.4, problem, bowling ball. Come on. Okay, so let me share this real quick. Share screen. Okay, so this is one of the PLC that's due this week, and it's just showing a bowling ball lifted to a shelf. And so the 4 different animations, basically, all of these are starting in the same spot, finishing in the same spot. So like this guy is going to go up, and end there. Animation 2 does a slightly different path, but the key here is gravity is a conservative force, which means it's path independent, which means all that matters is where it starts, where it finishes. So in this case, well, I don't want to give away the answer, but huge hint. So it asks you for what is the work done on the bowling ball and what is the work done by the external agent. So let me stop this for 1 second and then share with you a whiteboard. So for this particular case, you had basically somebody lifting a bowling ball from here and ending here. What I can say is the total work done by all external forces is equal to change in energy of the system. And right now we're only looking really at kinetic energy. So what I can say is the work done by gravity plus the work done by this external agent, you know, whatever hand is lifting it up. And the only thing we're looking at in this case is the change in kinetic energy. And since this thing starts at rest and ends at rest, the change in kinetic energy is 0. So the total work done is 0. So in this case, the elevation is increasing. The work done by gravity is less than 0. But the work done by the agent is going to be greater than 0. And however much negative work gravity does, that's exactly the same amount of positive work that the agent does. And the reason that's true is because the total energy of the system is not changing. So one, let me just give you a little preview for those of you who remember this from Physics 11 or earlier physics classes. Here, the potential energy of this, whatever this was, bowling ball or whatever, was increasing. But we're going to talk about this in a little bit. When I go and define a system, I have to define my system to include the Earth if I'm going to use gravitational potential energy as a form of energy. We'll kind of go through this, but anytime I'm including thermal energy, all objects that heat up must be included in the system. Anytime I'm doing gravitational potential energy, the Earth and the object have to be part of this system. And anytime I'm using elastic potential energy, the spring and the object have to be part of the system. I'm going to jump into that in chapter 10. So, went a little bit over. What I want to do is stop this. I'm going to stop this particular lecture right now. I'm going to restart this in about 3 minutes and open it up for office hours for questions. So if you have a question, come on back in a few minutes. I will answer some questions. And then, yeah, I'll have this video uploaded and posted later today. So hope to see you guys in a few minutes.